So good afternoon, everybody. Today in the GEOTOP-A seminar, we have Hannah Santa Cruz from the University of Amsterdam, who's going to tell us about Hodge Laplacians on sequence complexes. If you have questions, please put them in the chat. We'll be monitoring what you're asking. Hannah, please take it away.
Hello, everyone. Thank you to the organizers very much for the invitation. I'm very excited to give this talk and to Jose for hosting this. I'm going to be talking about some of the work that I did during my doctoral thesis with my advisor, Vladimir Itzkov. And so, yeah. So I'll begin my story by talking a little bit about my objective, which I believe is shared by many of us, which is just the idea of simplifying complex data. So just to give us a bit of a cartoon problem, one might be thinking about trying to solve the Netflix problem, right? So the idea would be in that case that we have a set of movies. And this set of movies might be given to us in what would be a vector representation, which is basically binary. So the dimension of our vectors could simply be the whole set of movies that we have recorded, which would obviously be very high dimensional. And then we just have a completely binary vector, which we would call a local representation. And so the problems with this, aside from the high dimension, is that it would be really hard to tell how these different movies relate to each other. And so we would like to transform these vectors into some other vectors which are hopefully much lower dimensional and that are also more easily to work with. So this is what we would call a distributed representation. So in the movie case, right, we might think about it like, for example, instead of just storing the name of the movie, we might be looking at what genre of the movie or how many male or female actors there are, or just like a bunch of characteristics like that, right? So once we have this transformation from a more local representation to a more distributed representation, we can actually work on classification problems. So for example, if we just wanted to do a binary classification, so that is to say whether a user likes or dislikes a movie, right? Then we might be given a set of movies that the user has already watched and his preference on it, either yes or no. And then we would seek to classify for new movies whether the user is expected to like it or not. And so this is typically what we call the Netflix problem. So today I'm not really going to be talking about movies. I'm really just thinking about simplifying these complex high-dimensional vectors. I just wanted to give you a little example to visualize. And so the main tool that I'm going to be using is spectral geometry. And so, of course, spectral geometry has been a very popular tool for a very long time. And a very classical motivation dates back to the 1800s, but was said very succinctly and nicely by Mark Kack in a 1960s paper. And it is, can we hear the shape of a drum? So that's just a very beautiful way of saying whether we could actually discern the shape of a region in space by simply looking at the Laplacian eigenvalues. And so why the Laplacian eigenvalues? Well, if you think of a drum as just like a taut canvas, right, with its border delimiting the shape of the drum, then that taut canvas can be modeled by the wave equation. And then if we look at the solutions of the wave equation, well, the Fourier coefficients would be these Laplacian eigenvalues. And so, in fact, these Laplacian eigenvalues are simply like the fundamental tones of the drum. And so they are indeed the sound that the drum produces. And so nicely enough, we already have the answer to this question. And it's not exactly, unfortunately, there are drums that one might say, or not, are similarly shaped that have the exact same eigenvalues. So we can't just use eigenvalues to distinguish drums right away, but still very fun to think about it. So like, for example, in this image that I have here, on the left, I have one shape, and on the right I have another, and I've have their eigenvalues, so you can see that they're increasing from the top row bottom, and you can see that they match exactly. And so this is why the eigenvalues wouldn't be enough, but they still do tell us a lot of information. For example, you can see I've colored these drums, right? And so the colors actually are representing the value that the associated eigenvector would be taking along this region in space. And so the blue cyan color is representing positive values, then black would be 0, and then yellow would be negative. And so you can see how the associated eigenvectors are changing as the eigenvalues increase. In fact, our eigenvectors become more and more varied throughout our region. And so this is what we describe as having just a higher Dirichlet energy. And so it's really quite nice to see how these eigenvectors vary through the region. So another like nice thing about these Laplacian eigenvalues in this like more like geometric setting is a very classical Weyl theorem, which tells us that we can in fact estimate the dimension, if not the exact shape of our region, by how these eigenvalues increase. So let's just name n of lambda, the number of eigenvalues that would be less or equal than a specific eigenvalue lambda. And then we're just going to take the limit of that lambda to grow, right? And we can see that the ratio of that number of eigenvalues, which is smaller, divided by lambda raised to half the dimension of our space, is actually going to be directly related with a coefficient that is purely dependent on the dimension of our space times the volume of our specific domain that our Laplacian is defined over. So that means that these Laplacian eigenvalues, even if they don't reveal exactly the shape of our drums, they can reveal quite a lot about the dimension. And these eigenvectors, we can tell that they're probably quite interesting and carrying a lot of information as well. And so moving forward, I'm going to be focusing on more combinatorial structures. So I'm going to leave the continuous domain, focus more on discrete. And so what we do here is we just extend that same Laplacian that we would have had in that continuous domain into combinatorial structures. And I'll start by extending it to just graphs, since I hope many people in the audience are more familiar with this. And then I'll start like changing domains until we reach sequence complexes, which will be the focus of this talk. So for graphs, we have here in the lower left corner just a cartoon example, right? And I've gone ahead and computed its exact Laplacian. And so the Laplacian is going to be computed very easily by just looking at the adjacency matrix to the left and then the degree matrix to the right. And so we just take the difference of those two, and that gives us the Laplacian, which is very simple. And so we can then go ahead and calculate the eigenvalues and eigenvectors for this graph Laplacian, and we will see that they're actually revealing quite a lot about the graph structure. So one of the first applications and more classical applications is just graph partitioning. Okay, so here what I have is this like very large graph, which actually has two very distinct regions. So we can see to the left this blue bulb, and to the right this yellow bulb, right? And so we would actually like to distinguish them. And so what we can do is we can associate a Laplacian matrix to this graph. And then once we do that, we can compute its eigenvalues and eigenvectors. And if we color the graph with respect to the values of the second eigenvector. So if I order the eigenvalues in increasing order, and then I take the one that corresponds to the second smallest eigenvalue, then this is going to give me a coloring here. And so since the eigenvector would obviously take a value on each one of the nodes of the graph. I can just color the nodes with that color. And so in blue, again, I've colored the positive values, and then in yellow are the negative values. And we see that this bulb to the left and this bulb to the right are completely distinguished vis-a-vis their sign. And so that's just like very useful and simple application of this Laplacian on the graph, which is great. But there you go. Taking it further from just graph clustering, we can also get embeddings. And so these embeddings would get us closer to that idea that I was talking at the beginning of getting a distributed representation from a more local representation, for example. So now imagine that you have a combinatorial structure, right? And so this combinatorial structure isn't embedded in the Euclidean space at all, actually, right? And still you can associate a graph Laplacian matrix to it, and then from that graph Laplacian compute its eigenvalues and eigenvectors, right? And so then if you, for example, take the eigenvectors that would correspond to the smallest non-zero eigenvalues, right? So say you take 2, this would directly give you just a two-dimensional embedding for your graph, since each one of our nodes was assigned a value for that first and second eigenvector that were associated to non-zero eigenvalues. And so that's very nice, right? And so to show that this eigenembedding has any interest at all, there's this beautiful theorem that Belkin and Nyogi put in a nice paper of theirs from about 20 years ago now, I guess. And so this tells us that if we have a graph, and this is a weight graph, with a weight matrix that is studying the pairwise similarity of our nodes. Then this embedding is in fact going to optimize preserving local information. So what do I mean by this? Let's call our embedding function y. So we're going to be taking our nodes, which were our vertices x, onto this embedding y, right? And then let's compare two nodes I and j, right? And we want to see if they were, for example, mapped far apart. But if they were mapped far apart, then we would have this distance here would be quite a large factor within this sum that we're trying to minimize, right? And so then, because this distance is going to be scaled by this weight, well, if this weight was very small, that would mean that the similarity of those two nodes was very small as well. And so it actually makes sense that they should be mapped far apart. Whereas if they were very similar, then this would be a large similarity value, say close to 1. And then this distance would weigh heavily on this objective function that we're trying to minimize, right? And so by just minimizing this objective function, we are going to be preserving this local information. And this theorem tells us that, in fact, the minimizing embedding would simply be the embedding that corresponds to this eigenvectors associated to the smallest non-zero eigenvalues. So that's really nice. Yeah, and so here I just have like a very traditional picture to show what I mean. So for example, we took this manifold, which is obviously a two-dimensional manifold, but is embedded in 3 dimensions to start with, right? We see that if we apply a traditional technique, say like PCA, right? PCA is trying to maximize the variance in between our nodes. And so it's actually just going to map it onto like an S, right? And so this S is basically collapsing all of the points onto basically really just a one-dimensional manifold. So that's not very useful local information-wise. And on the other hand, if we use this eigenmap embedding, then we actually basically unroll this manifold, and we get this kind of like horseshoe shape, I guess. And so obviously, like looking at the picture in globally, right, we have this horseshoe, which has nothing to do with the original S, right? So globally, it's not really preserving any interesting information, but locally, it has unfolded our dots, which is what's important to us. So yeah. So those are graph Laplacians, which are a very popular tool nowadays in like machine learning. And recently there's been a lot of work of extending these graph Laplacians to like higher order structures, such as simplicial complexes. So I'm going to be talking about that a bit. And the objective for me is that I'm eventually going to move over to sequence complexes. So sequence complexes are going to be directed structures. So for example, directed complexes would be a type of sequence complex. But in sequence complexes, I'm actually going to allow for repeated vertices, and I'm going to distinguish ordering. And so I'll introduce them a bit later, but for now I'll go into simplicial complexes. Great. Right. So for simplicial complexes, we can also define our Laplacian, and here it becomes much more natural why this is the Laplacian is. The definition is much more similar to the one that we would have in the continuous space, as it's going to just be in terms of this boundary operator. And as we could see, actually the graph Laplacian would correspond to this definition as well if one just reduced to the fact that a graph only obviously has nodes and edges. Right, so I just have the traditional definition here of a boundary operator over a simplicial complex, and then I'm going to also be working with the boundary adjoint, which is obviously going to be defined in terms of an inner product on my cochain space, which means I'll have to introduce an inner product, and I'll do that in a bit as well. But if you have our traditional coboundary and coboundary adjoint operators, then we can define the Laplacian as simply a sum of taking the composition of my coboundary operator with the coboundary adjoint, and then first taking the coboundary adjoint in lower dimension, and then taking the coboundary operator. Great. And so once you have this Hodge Laplacian, which we refer to for simplicial complexes, we can define our eigenembedding just like we did for graphs, which corresponds simply to taking the eigenvectors that go, in this case, from our cochain space onto a Euclidean space of dimension our choosing. And so I'll just make a note here that when we were working with the graph Laplacian, right, we were just embedding nodes, right? And now that we're working with this Hodge Laplacian, we can actually embed simplices of any dimension that we desire. So we could obviously still embed nodes, but we can also embed two-dimensional simplices or five-dimensional simplices, right? Whatever we like. And each of these is going to be associated to Laplacian of the respective dimension, and so there will be the respective eigenvectors and so forth. So there is really just a lot of power in this extended tool. And because of this, there's just been a lot of excitement, so I just wanted to refer the audience to just a sampling of papers that there's been, since it's really quite interesting field. Great. So now onto like my work. What I'm going to be doing is I'm going to be working with weighted complexes. And so this means that I'm going to want to define a metric for my simplicial complexes in this case, and then also for my sequence complexes. So this means that I want to define what I mean by two simplices being similar to each other. And so I'm going to think of this a bit geometrically. So if we think of like a geometric representation of our simplicial complex. So I'm going to think of this in the plane. Obviously, this is not always possible, but it's just for illustration purposes. So if we consider that each one of the nodes is a region in the plane, then I can consider the intersection of my regions, right, to be my simplices. So for example, a three-way intersection would be a two-dimensional simplex, and so forth. And so then if I want to estimate the similarity of two regions, I can actually just do this by computing the area of their intersection. Right, and so for example, here to the left, you might say that like blue region with that lilac region had a large intersection, right? Whereas on the right, the orange and the red region have a small intersection, which is in fact contained within that larger light green region. And so just like measuring all of these areas actually allows us to give weights to our simplicial complex. And so here I've just done that. So I took my simplicial complex and I've weighted it basically according to the intersection regions. And so by weighing it like this, I actually get a very nice weight function, since it's actually going to be approximating the probability of sampling said simplex, right? If we thought of sampling like by just like taking a straw in the plane. Right, and obviously the probability of sampling a simplex is simply going to be approximating the higher order correlations in between our vertices. So really, this is just like a very natural way of defining our weight function for these simplicial complexes. And so given this weight function, I can finally come back and actually define my inner product. So if I have my simplicial complex, which is weighed, and I consider the space of code change, then I'll just focus on the standard basis, and I'll define my inner product with respect to it. And I'm just going to define it quite simply as the inner product of an element of the standard basis with itself will be the weight of the corresponding simplex. And by doing this, I actually get the weights of these simplices appearing in my coboundary adjoint formula. So I have this coboundary adjoint formula here down below, and you see that quite naturally, I'm just summing. If I'm looking at the standard basis sum element of a certain tau, I'm going to be summing over all of the. I guess that's a mistake. That should have been a chi. Sorry. So if I was looking at the basis element of a certain chi, then over here I'd be summing over all of the chi minus one of its vertices, right? And then I'm going to be weighing this sum by simply the weight of my original simplex chi over the weight of chi minus set vertex, of course. Right. And so then once I have this weight function appear in my coboundary adjoint, it's obviously going to appear in my Laplacian. And so then when I take my eigenvector and the embedding, right, I'm hoping that this weight function is going to see itself very much reflected in this embedding. And so I will be just capturing all of that information. And so what I would like to show now, and this will be our first result, is that if there was no information behind my model, there would be, in fact, no information captured in the embedding that I produce either. And so to do this, I'm going to define a null model. And so this is going to be very natural for me because I have phrased our weight function from this probabilistic point of view from the start, right? So I'm just going to define what I call the independent vertices weight model. And so this weight model is going to be dependent solely on the vertices present in my simplex. So basically, if I have a simplex that has a set number of vertices, then I'm going to consider the probability of each one of those vertices of appearing, and I'm just going to take their product. So if one vertex appeared, that should not impact the probability of the other vertices appearing. It should not impact the probability of the non-vertices not appearing, right? I'm only going to take that very simple product, which is why it's called like the independent vertices model. And so if we take that weight function and we associate the Laplacian, we can actually explicitly compute the Laplacian representation for this null model setting. And we get the beautiful result, which is that this Laplacian is going to be, in fact, a multiple of the identity. And so this is, in fact, exactly what we would want, right? So basically, we have this statement which says that it's going to be a multiple of the identity, and this coefficient, which is multiplying it, is independent even of the dimension. So it's really quite as simple as possible. And it tells us that there are no interesting eigenvalues, no interesting eigenspaces. And so in fact, if you think about it, right, the associated eigenvectors, right, they'd just be like the standard basis elements. Those would be in the vocabulary that we were using at the beginning of the talk, just like the most local representation possible. So we revealed indeed no interesting information at all, and that is what we wanted since this is a null model. Right. So before I move on to sequence complexes, would anyone like to do any questions? No, we're good. Great. Okay, so okay, great. So right, so hopefully by talking about all of these like more standard results, we're all kind of like on the same page. And I won't lose you now. So I'm going to be focusing on what I call sequence complexes. And the objective of this is because there is data which does have repeated vertices, which does care about the ordering of vertices, right? And so, for example, on the left, I have this cartoon or a simplicial complex, right? If I wanted to distinguish the ordering, right, you might consider that I could just like order this face with little triangles. But of course, then it would get very complicated to visualize if I wanted to allow for different orderings of the same face, right? So the visualization gets a bit complicated there, and it gets even more, honestly, impossible to visualize with this sort of cartoon if you're trying to allow for faces that actually have repeated vertices, right? So this means that, unfortunately, moving forward, we are no longer going to have nice cartoons for our sequence complexes, which is quite sad. But yeah, we'll still have nice results. So let's give ourselves a simple example so that we can get an idea of why we'd have some sequential data, right? So imagine that I just have like a speaker and it's playing a note, and then I have a group of people in a room that are listening to the speaker. And I'm just going to record the order in which these people are listening to the sound. And so in this cartoon here, I would basically have Anne hears the sound first, then Bridget, then Chester, then Dave. Right. So I'm going to be thinking about a very simple, similar mathematical version of this, in which I have, instead of a speaker, a hyperplane, and instead of people, just points in the plane. And so basically, I have these points in the plane, and I'm going to be sweeping them with my hyperplane. And so what this means is I'm just going to be well, yeah, I'm just going to be taking the dot products, right? So for example, here I would have that the associated sequence to this point arrangement and this determining unit vector would just be A, then B, then C, then D, right? And so this is quite obvious because if I just take the dot product of this determining unit vector W with A, it'll be smaller than with B and so forth. So this is what I call a sweep sequence. And then the nice thing is that obviously if I just keep my same point arrangement and I vary my defining unit vector, I'm going to get a bunch of new sequences, right? And so this is what I call the sweep complex. And so the sweep complex is going to be an example of sequence complexes. We'll see in a bit, but let's just go through this first. So I have these 4 points, right? And if I just took all of the unit vectors along the whole unit circle, then I would in fact get 12 distinct sequences. And so I'll point out, for starters, of course, my point C is never going to be a lead in a sequence, right? It's never going to be the first one since it's kind of trapped in between the other 3, right? But also, this sort of sweep complex is in fact never going to have repeated vertices. So although it is a type of sequence complex, it's a very specific type of sequence complex because there's no repetition there. And so, yeah, so in this case, right, for our full-length sequences associated to this point arrangement, we would get 12 sequences. Now, to properly define my sequence complex in general setting, right, I am going to want to define it as a collection of sequences which is closed under inclusion. So of course, a sequence here is going to be allowing for vertex repetition. It is going to be distinguishing by ordering. And if I have a vertex at V and I'm looking at a specific length of sequence, I am going to be referring to the set of all of the sequences over that vertex set as just a curly S sub the dimension, which would be the length minus 1 of my sequences over V, right? Yeah. So then back to the sweep complex, what would happen here is that, of course, I have this point arrangement, which is 4 points, right, in space. And what I'm going to do is that I need to have it be closed under inclusion, right? And so obviously you can just close it algebraically, or you can actually construct it just geometrically by, for example, taking subsets of points. So if you were given this arrangement of 4 points, you could take the subset of points that just had 3 points, and you could sweep those 3 with all of your unit vectors, and then that would give you lots of sequences of length 3. But then, of course, you'd need to take all of the subsets of 3 points. So then these and these and these. And so you can see how these sweep sequences and more generally sequence complexes are going to be much larger than just simplicial complexes, right? Okay, great. So just like for reference, right, imagine that you had just 2 vertices. If you were dealing with a simplicial complex, then this would just be 1 edge, right? There's nothing else to do with 2 nodes. But if you're dealing with a sequence complex, then this can just go on as high dimensionally as you like. And even if we just truncate it up to dimension 2, you see we have all of these possible faces. So yeah. Are we good so far on questions? Okay. Good. So now that we've constructed this structure, which is of course like an abstract cell complex that we're calling sequence complexes, in our game, right, we like working with weight complexes. So the next step is going to be to introduce a weight function. And so similarly to how we did it for simplicial complexes, we're just going to introduce this weight function by first focusing on a probability distribution. So we're just assuming that we're given a probability distribution on our sequence complex, and how we're going to define our weight function is that we're going to take the conditional probability with respect to the dimension of our sequences. So basically, that means that if you looked at our whole sequence complex and you just summed the weights for all sequences of the same length, then that should sum up to 1. And so once we have that weight function, we can again define our inner product. So just like we did for simplicial complexes, if we are looking at the cochain space of our complex and we look at our standard basis, we're just going to define the inner product of an element with itself to be the weight of the associated sequence, as long as it was the element with itself, right? Great. And so then this weight is going to appear very nicely in our co-boundary adjoint definition. So I have here the definition of the co-boundary operator first. And so you can see that it's very similar to the co-boundary operator that we would have for a simplicial complex. Except for now we have a double sum, right? But this is actually very natural, because if you think of it for the simplicial complexes, right, all that you have to take into account is the idea of adding a vertex. But now actually it matters where you add that vertex. So now you have to sum over basically the length of your sequence. And of course, in this case, you can actually add a vertex that already existed. So even this sum is actually a bit longer. Right. And so then when you take your co-boundary adjoint, this one would be more similar to our co-boundary adjoint for the simplicial complex, since we're just talking about removing a vertex. And here again, we have that it is multiplied by this ratio of the weight of our original sequence, and then the weight of the sequence minus that vertex that was eliminated. Great. And so again, we have this Hodge Laplacian, which is going to very nicely operate in between our cochain spaces of a specified dimension, right? And so again, it is just this nice sum of the composition of our boundary operator with its adjoint. And because our Laplacian is going to be operating in between these cochain spaces of a specified dimension, this means that we again have a very powerful tool because we can now choose to embed sequences of any length. So for example, we started out by embedding just nodes, right? And then we were embedding simplices. Now we can embed sequences of any length. And so we can have our vertices be repeating, our vertices be ordered. And other than that, it's basically the exact same framework because we're just going to choose a dimension of our choosing for the embedding. And then we can just embed into those first k eigenvectors that are associated to non-zero eigenvalues. Great. And so at this point, I would just like to illustrate that this embedding is actually worth looking at, since I've already talked through all of the construction. So what I'm going to do is I'll just go back to that sweep complex that we were thinking about earlier, and I'm just going to model it. So what I'm going to do is I'm just going to do an example where I took a fixed number of unit vectors that are going to be defining our hyperplanes. So I took 1,000, and then I took 23 points that were randomly sampled in the plane. And so what I hope to do is that I'm going to build this whole sweep complex like we described earlier, and I'm actually going to try to reconstruct the geometric arrangement of my unit vectors that are defining this sweep complex. Right. So for example, here I have like 4 points highlighted, and then I would have this like unit vector, right, and it would just go like sweeping. And so I highlighted 4 points because I am in fact just going to do my experimental results with sequences of length 4 being embedded. And so that's kind of just to prove that like that is good enough. But yeah, obviously higher dimensions is very fun and also more expensive. So what I'm going to do is that I'm going to group the sequences by which unit vector generated them. So of course, since we're looking at a total of 23 points, but then we're only going to be embedding length 4 sequences, then each unit vector, right, is going to be generating many different sequences of length 4. And so that means that I'm going to have all of these like collections of sequences, which I would call like x of w, right, of a specified length. And so my objective here is to reconstruct the arrangement of my unit vectors w. So of course, I'm not going to actually remember which w it was that generated this bag of sequences. I'm just bagging them together. And I'm going to bag them together for basically all of the dimensions up to length 5. Right? And so that means that I'm going to get a sequence complex out of this that is going to be length 5. Oh, sorry, dimension 5. Sorry, the highest dimension for, so the longest length is 5. And that is because since I'm only going to be embedding the length 4 sequences, I don't actually need, well, a higher dimensional complex, which would be more expensive to compute. And so the other thing that I need for my complex is to associate the weights, right? And so I'm going to associate the weights in a very standard fashion, basically by looking at the frequency of sampling. So remember, when I have my arrangement of 4 points and I'm sweeping it right with my hyperplane, then obviously there might have been several hyperplanes that would have swept my points and yielded the same sequence, right? And so since I have here a finite set of unit vectors that are going to do the sweeping, I can actually just count how many unit vectors generated the same sequence. And so that's just going to give me a very natural weight function for my sequences, right? And so then once I have that weight frequency, I can just normalize it so that, again, I have that all of the sequences of the same length add to 1. And then this is going to give me a sequence complex, which is weight that I can actually apply my machinery to. So if I compute, for example, the three-dimensional Laplacian for this sequence complex, then I am going to get an eigenembedding of, I'm going to go for dimension 5 eigenembedding for all of my sequences of length 4. Right? And so now the thing is, I said what I was trying to do was recuperate the arrangement of the unit vectors that generated my sequences, right? And so far, I actually have an embedding of my sequences, not of the unit vectors. And so what I do here is just the simplest possible step. I'm just going to take an average. So remember that I actually know all of the sequences that came from a same unit vector. So what I'm going to do is I'm going to associate an embedding to that unit vector, which is just the averaged out embedding that was associated to all of the sequences that it generated, right? That were of the same length. And so then this would give me an embedding for still length 5 for each one of my unit vectors. And then finally what I do, just to produce a nice image, is to compose it onto its first two principal components. So that we can see here. To the left, that we do in fact get back that nice circular arrangement of our original unit vectors. So remember, the only thing that we are feeding this algorithm is just the sequential information of what order my 4 points were swept in. And so just from the sequential information, I do get back the circular arrangement, which if you look to the right image, where I'm just comparing the inferred angle with my true angle, then you can see that it really is quite a straight line, right? So it is, I'm recuperating quite a lot of the original arrangement. And so I might extend this to just like a simple conjecture, which is that if I actually had as many points in my plane to sweep as desired, then I could actually fully recover the local information of my unit vectors, which are generating these sequences. So that's what I have here, and I could even hopefully do this for any dimension desired, not just the plane, right? Right. So that's just like a nice little example that shows that these eigenembeddings are really like capturing the nice information that's behind it. But still, we would also like to show is not only that they're capturing the nice information, but they're not going to capture and throw out a bunch of noise as well. And so to do that, I'm just gonna go back to that idea that we had earlier of this null model. And since again for this sequence complex, we've done our weights from a very like probabilistic point of view, we can very naturally define a null model for this case too. And so this is going to be the big result of our talk. Great. So in this case, I'm going to define the independent vertices model for sequences, very similarly to how I defined it for the simplicial complex, by simply looking at what are the vertices present. So in this case, right, I'm not going to be considering what was the last vertex to appear, and does that change the probability of the next vertex appearing in my sequence, right? I just care about the vertices. I don't even care about the ordering. So I really am like just losing a lot of information there. So it's really quite a simple model. And so given this model, I can, just like I did for the simplicial complex, actually explicitly compute the representation for my Laplacian. And so we see here that we get a pretty simple representation, really. So considering that the Laplacian on sequences is quite much more complicated than the simplicial, and the Laplacian on simplicial complexes, all to be expected here. And just to like unwrap this a little bit, here on the left we have obviously the diagonal terms, and so you can see that unfortunately they are not a scalar multiple of the identity, even the diagonal ones. And then even worse, we also have off-diagonal terms. But we actually have very few off-diagonal terms, and so these off-diagonal terms are actually just all involving the sequences that just differed in one vertex exactly from the sequence that we were evaluating. So really quite similar here. And so yeah, although this is not a diagonal matrix, it's not too complicated, right? But well, unfortunately, this representation doesn't really tell us anything about our eigenspaces. So we had to compute those just by themselves. And we do have an explicit computation for them and of the eigenvalues. And so the spectrum is just really quite beautiful. So if you just took like a regular sequence complex, right, and you associated some weights and then computed the Laplacian and its eigenvalues, then of course the eigenvalues would just be completely spread out, have very low multiplicities, right, and be just all over the place. And in the case of taking the full sequence complex with these just independent vertices model weights, you actually get only integer eigenvalues, which is quite great. Obviously, normally you do not have integer eigenvalues. And moreover than that, you have very few eigenvalues. So for a fixed dimension n, you are in fact only going to have n plus 2 eigenvalues. And so that is quite great. And we even have like this very simple formula that is relating the number of eigenvalues to this dimension and also to the size of your vertex set. So yeah, that's really quite nice. And just as an example, right, given that these are our eigenvalues, let's just look at the associated eigenvectors for just the smallest eigenvalues. So those are the ones we're normally interested in. Well, the number one eigenvalue is actually just having multiplicity 1, and it is just associated to the constant cochain. So its eigenvector is really completely boring. So this is basically the equivalent of the 0 eigenmode for the graph Laplacians. And then when you look at the eigenvalue 2, then you have already a really high multiplicity. So you basically have your dimension times the size of your vertex set, almost. And so what these associated eigenvectors are going to do is they're just going to be highlighting for the sequences if there is a specific vertex at a specific spot. So basically, these eigenvectors are just a completely local representation. So going back to what we were talking about at the beginning, this is just like definitely not capturing any interesting information. This is not giving us a distributed in a representation that we are all interested in. It's just telling us this is boring, which is exactly what we wanted. Right. And so yeah, so I even have like the explicit definition here. So for eigenvalue number 2, what you would need to do to come up with this explicit definition is you would just want to fix one vertex A of your whole vertex set. And then basically what happens is all of your eigenvectors are going to highlight, each one is going to highlight a different vertex. You're just never going to highlight A at all of the possible spots along your sequence. Yeah, and so yeah, so just to like wrap up our talk, and since we started out with some classical motivation, I'll just bring back a classical theorem. We have like the Ekman theorem from like 1960s again, which is telling us that in fact the kernel of the Laplacian gives us this like very beautiful way of in fact computing the cohomology of complex. And so that means that since we've already computed explicitly the representation and the eigenspaces of our Laplacian for this independent vertices model, we have in fact already basically done all the work and figured out the cohomology for the full sequence complex, which is quite nice. So we have that the full sequence complex does in fact have trivial cohomology. And this is easy to see since we know that our Laplacian has a fully integer spectrum with eigenvalues starting at 1. We have no 0 eigenvalue. We have a trivial kernel, and that means that we just have a trivial cohomology for the full sequence complex, which is quite nice. And so yeah, that's just nice combination of very classical theorem. Great. And so yeah, I'd like to hear if you have any questions.
Thank you, Hannah. So let's first thank the speaker. If you can, please unmute yourselves, and we'll just give her a round of applause. So let's open up the floor for questions. Yeah, so if you have any questions, you can either raise your hand using the Zoom features. You can put them in the chat. And I'll ask the first question while people get ready. So Hannah, beyond the fully independent model, do you have any other guesses for models where you have correlations between the vertices?
I'm still unmuted, right? Yes.
You're unmuted, yeah.
Yeah, okay. Yeah, so I've been working on studying, for example, like a model that would be based on like Markov weights.
Mhm.
And there is like some nice patterns there, but I haven't like really gotten anything quite as beautiful yet. So yeah.
I see, but the hope is that the complexity of the spectrum should
Yes,
capture some of the complexity.
the complexity of the spectrum definitely increases already greatly for the Markov case. But yeah. I've been working on more like applications with like real data as well, and so yeah, of course you can see the complexity of the spectrum skyrockets.
Great. And then for the example with the circle,
Mhm.
the first, let's say you did it with dimension 5. You went into
Mhm.
R5 and then did PCA.
Mhm.
So how bad is it just to do the first 3 eigenvectors for the embedding instead of the first 5?
Yeah, I realized that I probably should have generated the picture again for dimension 2 because I could have done it with just dimension 2 and it really is almost as good. And I think actually like it kind of like detracts by uh doing the PCA, but like how magical just the eigenmaps embedding is already. So yeah, like it's a little bit less nice, but not much. Yeah.
Okay. Do we have any other questions? Again.